All right, we have here a sample from the optimization packet. We started to present it in class and there was a little glitch, and I went over and looked, and it's just kind of a trivial algebra mistake. So I thought I would at least show how to do this problem in which we're proving that the maximum area under a 10-foot ladder is going to be when the triangle that's made is an isosceles right triangle. Okay, you can kind of do that thinking like a soap bubble. When would you equalize sort of the pressure, so to speak, of the soap bubble is when you're going to equalize these two legs of the right triangle. But to prove it mathematically, and to do these problems in general, I think it's useful to go through it step by step. So start with like your basic area problem. We're trying to maximize the area, so we start off with that area. And then we're going to try to write base and height in terms of x, okay? Well, the base is just x, so that's easy. The height then we can solve using Pythagoras. 10 squared is 100, take away x squared, square root it. That's what that height would be for Pythagoras. I sub that in. Now I'm going to take the derivative of this, and then I'm going to set that equal to 0. Well, when you see the 1/2 out there, and you know that later you're going to take the derivative, you could, if you're just working quickly, just ignore that because we don't need it. Because once we set it equal to 0, we can just multiply both sides by 2. Also a constant, you can pull that out of any function you're going to take the derivative of. So it's a little trick that can save time rather than getting messed up with fractions. So I'll just take that away, all right? Then when I take the derivative of this part, it's going to be this times the derivative of that. So just be really careful. That's something to the 1/2. Bring the 1/2 out front. Don't mess with that inside. When you take away 1 from the 1/2, it's minus 1/2. There it is in the denominator to the 1/2. But then don't forget to take the derivative of the inside. That's a minus 2x. Okay, when you bring that 2, there's the minus 2x. This 2 cancels with that 2 from the 1/2. Okay? And we've got that x out front, so that becomes x squared. Turns out it's going to be a negative x squared, but we'll get rid of that in a second. Then it's this times the derivative of that, I've done it, plus this times the derivative of that, which is just a 1, okay? And here I have the derivative then. I'm going to set this equal to 0, and when I set this equal to 0, then I can move this over, and it becomes 1/2. So that is gone, all right? So it becomes, the 2's have canceled, I've got x squared over 100 minus x squared is equal to this. And when I cross multiply to solve it, I get my x squared is equal to, the radicals go away, it's very nice, 100 minus x squared. I just ran out of space, so I moved it up here, add x squared to both sides, and then I solve, and I get x is equal to the square root of 50, or 5 radical 2. That makes a lot of sense because both of these then will be 5 radical 2, which is what we expected. Okay? Simple little problem, good illustration.